for the presentation. Okay, continue. Yes. So my apologies to everyone for last week. I was unaware of this different time change.
Yeah, I didn't realize we do it a week later than Europe.
Yeah.
I didn't know you guys did it at all. I thought it was something to do with our farmers or something, but yeah, anyway.
Anyway, shit happens. So this is the second lecture about this generalized Ricci flow, and just let me start by recalling you what this is. So we are talking about geometric flow on manifolds for a pair given by a Riemannian metric GT and a two-form BT, a one-parameter family of those. And the flow is defined as follows, as I introduced in the very first lecture. Here, what you need to do is to fix one cohomology class, represented by H0, which is a closed free form. And then what appears in the right-hand side, which dictates the evolution of the metric and the two-form, is on the one hand -2 Ricci. So this thing is, these two terms here are the usual Ricci flow. And then plus h squared, half h squared, which is h is a free form in the same cohomology class that you cook up out of H0 and BT. And h squared is this quadratic tensor in H. And then the evolution of the two form is by minus the adjoint of the stereo differential with respect to the metric, which is calculated in an orthonormal basis by this. So the other day I introduced a bit the motivation coming from physics, from two-dimensional sigma models, and I also mentioned some like paradigmatic examples where you can see that there are qualitative differences between the usual Ricci flow and generalized Ricci flow. So what I want to talk today first is about the symmetries of these equations and their relation with current algebras. Okay, and then once I talk a little bit about this, I will move on to talk about general geometry. So current algebroids were introduced by Liu, Weinstein, and Chu, building on work by René Dorfman and Ted Courant. And as observed by Pablo Cervera, they play an important role in the theory of two-dimensional sigma models. So recall that this theory, this physical theory for fields given by maps from a surface into a manifold is the origin, or is the physical origin of the generalized Ricci flow equations that we are considering. So let me recall what this structure of a current algebroid is. So given a smooth manifold, you can consider the tangent plus the cotangent bundle of the manifold. And this has a canonical split signature pairing, given just by pairing vector fields with one forms. So if you choose a closed free form on the manifold, then we have a Dorfman bracket, which is written like this. So it's cooked up out of natural operations in the vector fields and one forms. So the first bit is the Lie bracket, the second is Lie derivative of x of eta with respect to x, and this other term. And then it has a twisting term coming from this closed free form, given by contraction of the vector field x with the vector field y. So one of the nice features of this structure is that puts into place an enhanced group of symmetries. So not only diffeomorphisms are going to play a role in this story, but also a new type of symmetry called B-field transformation, which is given by shifting. You choose a two-form B, and then you shift x plus c to x plus c plus ixb. So this is contraction of B with the vector. And one can see that if B is closed, this preserves this full structure. So it's very simple to check that this is just for the just for being a two form, this is going to preserve the pairing. And then for the bracket, you need to impose closeness on the two form. And then this simple structure was then axiomatized by Liu, Weinstein, and Chu, leading to the very general definition of a Courant algebra that I'm going to introduce in the next slide. So let me go for that. So a Courant algebra, as I said, this is just an abstract version of what I introduced before. It's a vector bundle E over a smooth manifold M, equipped with a non-degenerate symmetric linear form. In the case of our interest, the signature is going to be NN, where N is the dimension of the manifold, but more generally, it could be arbitrary signature. Then you also have a bracket on sections and a smooth bundle map from E to the tangent bundle called the anchor map, which is something that fixes your object against the manifold you are dealing with. And the equations or the axioms which are satisfied by these three geometric components are the following. So the first one is just saying that the bracket satisfies the Jacobi identity. So the second one is that the anchor map has to be bracket preserving with respect to the Lie bracket on vector fields, and this abstract bracket that I told you. The third one is that the bracket acting on the second component is a differential operator of order one. This one tells you that the bracket is naturally orthogonal with respect to the pairing. And the last one is a bit mysterious because you see, if I impose that the bracket is skew symmetric, then automatically I get a Lie algebra. But here I'm telling you that the bracket may not be skew symmetric. Actually, the failure of this being skew symmetric is precisely D of the pairing. Okay, so this is very abstract and very general definition. But if we consider the case of exact Courant algebras, this is the case where the sequence induced by taking the dual of the anchor map. This takes T star to E dual, and then identifying E dual with E via the metric. This sequence is exact. So we have 0 T star E. Then in this case, we are back to the example that they put in the previous slide. Okay, so just let me go back 1 minute to tell you that this thing I showed you here is all you can do for the case of exact Courant algebras, essentially. And I'm going to explain that in a minute. So to see this, let me state the following theorem, but for this I need a definition first. So the theorem is a classification of exact Courant algebras, and then I need to tell you what are the morphisms, what is an isomorphism of these guys. So an isomorphism of Courant algebras, E and E prime over the same manifold M, is given by a pair F, small f, big F, where F is a diffeomorphism on the manifold, and then big F is an orthogonal vector bundle isomorphism from E to E prime, which exchanges the Dorfman brackets. And then I'm going to say that this is small if little f is in the component of the identity for the diffeomorphism group. Okay. Then there is this nice theorem by Severa, which tells you that essentially what I showed you in the first slide is all you can do for these exact Courant algebras. So then the set of isomorphism classes of exact Courant algebras modulo a small isomorphism is in one-to-one correspondence with the third cohomology group of the manifold. So this means that whenever I give you a closed free form, this has a natural representative, and then up to isomorphism, this is going to correspond to the rank homology class. Okay, so before I go on, yeah, let me tell you just first this thing. So given a cohomology class in H3. Then if you take a representative H, then we can cook up this model. This is what I said in the first slide. But I would like to go a little bit through the proof of Severa's theorem. I think this is illustrative of what happens for these subjects. So let me go through that. I'm going to change to the other laptop if I can. Okay. Now I had a, oh. Yes, 1 minute. Sorry about that. So what I want to illustrate is this lemma here due to Marco Gualtieri, which classifies all the automorphisms of E explicitly. And for this, I want to give you a proof of Severa's theorem. Any questions so far? Okay. Good. Almost there. So. Okay. Good. So now I'm going to stop sharing here and I go to my other laptop because I can write on the screen. So let me go stop this and yeah, and let me share. Are you Jeff? You have to allow me to share with this other user.
In just a moment.
Yeah, now I'm fine. Good. You're there. Do you see my whiteboard? Can you see it? Yeah.
Yeah, I can see it.
So what I want to show you is this classification theorem by Severa. So what happens is the following. So I want to prove that the isomorphism classes of exact Courant algebroids are in one-to-one correspondence with the third cohomology of the manifold. And recall that this notion of isomorphism is via a small isomorphism, meaning that I have this diagram and here induced, well, this is little f and this is big F. So this diffeomorphism in the base is in the identity component for the diffeomorphism group. Okay. So this is what I want to
to prove. Okay, so this is then the notion of isomorphism. So what happens is that if I take an E over M, which is exact, then I can take an isotropic splitting of the sequence which defines my exact Courant algebroid S. This is the isotropic splitting, so it means that S with S is going to be 0. And then once I take this isotropic splitting, this induces an isomorphism determined by S between E and tangent plus cotangent in such a way that the induced, well, what is this? Let me call this, let me give it a name, psi S. So psi S is implicitly defined as follows, when the way defined is psi S minus 1 x plus t is going to be S of x plus a half of pi star of g. Okay, so pi star, recall that this is pi, this is the anchor. I take pi star, I go from t star to e dual, and then I identify e with e dual. Okay, so this is the isomorphism. So with this isomorphism, the pairing is the canonical one, and then the bracket corresponds to the bracket for a choice of 3 form which is closed. xy plus lx eta minus iy g plus iy ix h. And here h is some 3 form on the manifold which is determined by the split. So essentially, this h at in x, y, x, y, and z is given up to normalization by s of by sx, sy, sz. This is a y. Okay. So this form of the bracket and the pairing, I didn't tell you, right? But this form of the bracket and the pairing using this isomorphism follows from the axioms. You can keep track or trace the form by just applying the axioms once and again into this particular model. Okay, so because our 3 form H is closed, we can associate its class in the round cohomology. And this is going to be what assigns the isomorphism class of the Courant algebra. Is going to be determined by this thing. So why is this well defined, and why any other element is also, which is isomorphic to it, is going to be in the same cohomology class. So first, well defined. So recall what I used to define this from my Courant algebra is the choice of an isotropic splitting. So if I choose a different one, you can check that this is going to be S plus e to the b, where e to the b is one of these b field transformations. So we call that e to the b x is x plus ixb, and it does nothing on the cotangent band or on the cotangent line state identity. And now what you can check is that if your S induces this particular H via this formula here, then your S prime is going to induce H prime, which is H plus dB. And this is just a calculation using the natural properties of the Lie derivative and the Lie bracket and the exterior differential. Okay, so this tells me that the cohomology class is well defined. So secondly, and this is what really has most of the content of the proof. What happens if I take now E prime, which is isomorphic to my E? Well, recall that what is going on is that I have this orthogonal bundle isomorphism and some F in the identity component of the diffeomorphism group of M, and this is a bracket preserving. Then what you can prove with a little of care is you can prove that there exists a two form on the manifold such that after identifying E with tangent plus cotangent with bracket with canonical pairing and bracket given by some H, this is by choosing an isotropic splitting as before, and after identifying E prime with the same thing, tangent plus cotangent, pairing, and the bracket given by a preform H prime, by choosing another splitting S prime, then what happens is that this B satisfies the following: F star H prime minus H equals to dB. This amounts to say explicitly what is this F in this particular model. So what happens essentially is that F is of the form e to the B, no, it's the other way around, is of the form in matrix form F star F star e to the B. It has this form. You can prove that it's always this way. And this is the condition for the bracket to be preserved by this. Okay, so with this formula in hand, this F star H prime minus H equals to dB, then you can prove that the cohomology class of H prime and H is the same because this F is in the identity component of the diffeomorphism group. So recall we have F star H prime minus H equals to dB, and then just because this F is F1 for some one parameter. Then just taking, applying the fundamental theorem of calculus here, you have that H plus dB equals the integral from 0 to 1 of the derivative this is an S, and this thing is the Lie derivative of with respect to the one parameter family of vector fields generating ft of H prime, but because H prime is closed, this is just T of IXT, which is exact. And now you can apply, you can exchange D with the integral and you obtain that the class of H prime equals. Okay, so this is the idea. Any questions about the proof? Okay, so if not, let me go back to my slides to show you now what can we do with this. One thing we can do is to uncover the symmetries of the generalized Ricci flow. Okay, so let me go back to this. Just 1 minute. Compose. Anyway, I need to change computer again. Sorry, Jeff, you need to allow me to share from the other Mario.
Oh, sorry.
now
Yeah, I already made you co-host on 2 of them. Is there a third
Okay.
computer?
No, yes, no, these two. Okay, it should be fine.
By the way, maybe I just ask a general question.
Okay, good.
Is it possible to have like a?
So are you with me? Do you see the slides?
Yeah, you have 2 sounds coming through though. Maybe
So
you
if
want
so,
to-
okay.
I was
Do
just
you
curious if
hear
it
me
was ever.
properly?
Yeah, we can see. Yeah.
So with the formula that I showed you before,
Wait, Mario, can I just
Then,
ask briefly? Or
you can easily calculate the group of automorphisms of an hexagonal algebroid as follows. So the group of automorphisms of phi, following the same argument as before, is of the form pairs FB pairs FB such that F is a diffeomorphism, B is a 2-form on M, and then F star of H minus H equals D of the 2-form. Okay, so the more general symmetries are not given by closed 2 forms, but by this twisted thing. And this is the natural group structure. Okay. Is there, so someone is asking something on it?
can you hear me, Mario?
Yep.
Okay, I don't know. That was strange. In any case, I asked a question. It seemed like it didn't get through, but it's okay. I was just curious if there were like natural situations where you could have like a non-small isomorphism of Courant algebroids. Is there some like obvious natural case where that happens?
Yeah, I guess. Yeah, this question is maybe important for like collapsing phenomena or things like that. Because nothing tells you that your diffeomorphisms have to be small. They are just arbitrary diffeomorphisms between 2 manifolds. And in that case, there may be something. So there may be some mapping class group action doing something funny on the cohomology class of the 3. So a priori, yes, and it could be related to collapsing.
Oh, that's interesting. Yeah.
Okay. So with this explicit description of the automorphism group of E in hand, the first proof of this is, I think, with Marco Gualtieri in his thesis. Let me state the following result. So this has been proved by several people, and here I just summarize what we know so far about the symmetries of the generalized Ricci flow. And the idea is the following. So the generalized Ricci flow, as I stated it before, for the evolution of a metric and a 2-form, and H being this 3-form evolving in the cohomology class, and this other quantity, which I presented in my first lecture, which is like the generalized Ricci flow under natural assumptions and well understood is like a gradient flow for this function. But you need to involve another quantity, which is a function. So these two quantities are preserved by the group of automorphisms of the exact Courant algebroid, given by fixing one of the closed three forms in the cohomology class. And as you see, well, let me first comment on this formula, because I said it the first day and there have been 2 weeks. So this formula here is given as follows. So this is a function for a metric and a two form. So these are the unknowns of generalized Ricci flow. But then you have another ingredient, which is a smooth function on the manifold. And the formula for the functional is that the scalar curvature minus 1/12 of the norm square of the free form plus 2 Laplacian of f minus norm square of the gradient. And then it's not the metric it's not the volume of the metric what you need to use for integrating, but this twisted volume using the function itself. Well, the nice thing is that after gauge fixing, and this has to be understood in the generalized sense, this generalized Ricci flow is a gradient flow for this generalized Einstein-Hilbert action. And at least to me, it's kind of surprising the first time you see this thing that, or not completely obvious, that this natural flow equation that you can cook up for a metric and a two form is actually preserved by this group of symmetries. Right, it's diffeomorphisms and two forms, which have to preserve the class of H in the following very special sense. So f star of H minus H is D of the prescribed. Okay, so this is kind of nice. And now I would like to go into the proof of this observation. I didn't mention it, but I stated here. But this is in different, chopped into pieces. This is due to Severa, Balagh, and myself, and Jurko Vysocky, and also in my work with Stritch in the book about generalized Ricci. And our proof, at least of this second part related to generalized Einstein-Hilbert action, is based on a nice paper by Waldron, Coimbra, and Strickland Constable. So in the rest of my talk, what I want to do is to give you a hint on why this is true and which enhanced information do we get if we understand the proof of this. So why this is going to be important for us? Well, it's going to kind of specify a route to follow, because once we know what are the natural symmetries of the equations, then we can do several things. One is to have a natural notion of gauge fixing to keep track of symmetries. This will also naturally lead us to a notion of solitons, and this is of key importance because solitons are going to be like limits when t goes to infinity of infinite solutions of the flow. And then also we would allow us in due time to define flows or versions of generalized Ricci flow which are naturally adapted to complex geometry, in particular pre-closed and generalized scalar Ricci flow. And also another important upshot that we're going to obtain out of this theorem is that the equations are preserved under some natural symmetry which was discovered by physicists in the 90s, and it's called T-duality. And this is originally a quantum symmetry. It's a symmetry of the sigma model as a quantum theory, but it has some geometric shadow, and we're going to see that and there are some natural geometric consequences of this. And to finish this part, I would like to mention that we find a hint on this result. So why these Courant symmetries are like the natural symmetries of generalized Ricci flow in the work by Severa, where he explains what is the relation between Courant algebroids and two-dimensional sigma models. So the idea is very roughly the following. So remember that 2 weeks ago I told you that generalized Ricci flow was appearing as a sort of renormalization group flow for a two-dimensional sigma model, the fields of this physical theory are maps from a surface into some target manifold, where our current algebra is going to be. And part of the action, not all, but part of the action was given by this West-Sumino term. So given a two-form on the manifold, you can think of these two forms as a Lagrangian for maps from the surface, from a surface into M, which assigns to one of these maps the integral of the pullback of the two form on sigma. And recall, this was part of the action of the sigma model, which was mimicking the bit in the Lagrangian for magnetic geodesics, if you recall what it was. So if you do a calculation of what are the critical points, these are going to be given by vector fields along the map phi, so it means sections of the pullback of the tangent band along phi, such that the contraction of this vector field with the three form is 0, where the three form is nothing but d of the two form that you used to calculate the Lagrangian. Is the three form which determines the Lagrangian. Okay. And an interesting observation is that you see, even though the functional itself depends on the two form, the critical point equation, so the Euler-Lagrange equation, only depends on d of v, on the field strength of the two form. So it means that we can regard solutions of these equations for a closed free form as some sort of critical points for some two-dimensional Lagrangian problem, even if it is abstract. What I mean is that even if H is not the exact, you can think of abstractly as solutions of this equation as some sort of solutions for some two-dimensional Lagrangian problem. And yep, sure.
Is the critical point equation that's for all x that are tangent to the map?
Yeah. I didn't say what x is, but this is, so when you take derivatives of this, so what is an element in the tangent to the space of maps? This is a vector field along the map, right? And then this equation is for x along the map phi. I don't know, probably this is not the best way of writing this equation, because I wrote a pullback. Maybe this is what is confusing you. I wrote a pullback of.
Isn't the critical point a map? It's supposed to be a map such that so it should be.
Oh yeah. Oh, sorry. Yeah, I understand now your point. So the critical points are maps, says that for any x which is tangent to that map, phi star ixh is 0. Yeah.
Okay.
Yeah.
Thanks.
And what I'm saying is that this equation makes sense even if h is not the exact. Yeah, the critical point is the map, not the. Sorry about that. Okay, so because of this critical point equation, you automatically find some special symmetries of this functional, which are given by vector fields on the manifold, not only along the map, but vector fields on the manifold, which satisfy that if I contract the three form with x, this is d of a function. So this is a two form, and I declare this to be the exact. If you have this equation, right, then of course, this is going to give me directions in the space of maps. So if I have one of these vector fields, deforming a map along this vector field using its flow is going to give me a direction where my functional does not vary. So these are natural symmetries of this function. And the nice thing now is that out of this equation here, if I have a vector field which satisfies that the contraction with H is D of a one form, then I can cook up naturally an element in the Lie algebra of the automorphism group of tangent plus cotangent with this twisting by H. And this is x plus dg plus ixh. So this means that symmetries of the two-dimensional variational problem that I'm considering correspond, at least some of them correspond naturally to the symmetries of the current algebra.
Sorry, Mari, can I just ask something quickly?
Sure.
Like, just so I'm sure I understand, like when you say symmetries here, so yeah, so you have a vector field on M, IXH is D exact, then I should think of like perturbing B by the
No. What
difficulty
I'm saying,
generated
no.
by X, or
What I'm saying is that if you take one of these maps from sigma to M,
yeah,
and deform it by the flow of this X satisfying this equation,
oh,
then the functional doesn't vary.
so it's kind of like, oh, okay, so it should like produce like a family of critical points.
Yeah.
I see. Yeah. Okay.
And then these natural symmetries of the Lagrangian for a given H, these natural symmetries of the Lagrangian for a given H, are going to give you are going to be in correspondence with the symmetries of your current algebra. So in a sense, your current algebra is a way of codifying natural symmetries of the two-dimensional variational problem. That's my point. It's a geometric way of doing that, even though it is like kind of taken from the heart, but it's a natural way of codifying the symmetries of the two-dimensional variational problem, which is hidden in your problem for generalized Ricci flow.
I see.
Yeah.
Why do you add dxc to IXH?
Can you say it again?
Why, for the Lie algebra element, why do you add dxc and IXH?
Yeah, sure. Let me show you that. So you see, if I take this element, the two form B is dg plus IXH, right? So if I take D of the two form, if I take D of this part, what this is equal to is to the Lie derivative of H with respect to X, right? You see what, if you take D of these two form here, so I have dg plus IXH, you take a stereo differential, this goes, and you just obtain Lie derivative of H with respect to X. Right, so what is the group of automorphisms? I showed you here. The group of automorphisms are pairs FB, such that the pullback of H minus H is dB. So the Lie algebra is given by vector fields and two forms, such that the Lie derivative of H with respect to the vector field is D of B. So this is why you need to twist by IXH in order to get an element in the Lie algebra. Okay. Is it clear? I can write it on the whiteboard. Does it help if I write it, Francis, or is that okay?
Well, maybe why not? Yeah, go ahead. If you don't mind.
I write it?
Please, yeah, please.
Yeah. Oh, okay. Yeah, sure. Shifting again. Okay, stop here. Yeah, let me show you. Yeah. Yeah. So the defining equation for the, do you hear me? Is that okay?
Yep.
Do you hear me?
Yep.
Yeah, okay. The defining equation for the automorphism is and this is, so an automorphism is a pair FB
So it means that the Lie algebra is for pairs xb or x manifold. And you take derivatives of this, what you get is the defining equation for an element in, right? I'm telling you that there are special symmetries of my Lagrangian which are given by vector fields x such that ixh equals to d of g for some 1,4. So it means that if I take a map and I deform it with the flow of this vector field, then the function does not vary. And what I'm saying is that out of these special symmetries, I can cook up a Lie algebra element in the Coulomb algebra, in the automorphism group of the Coulomb algebra, which is x plus dg plus ixh. So if I call this B, this defines an element in the Lie algebra because d of P so defined is d of d of t is 0, because this is the stereo differential squared. This is dixh, but because h is closed, this is lx. Okay.
But
So
I thought
this guy here, yep.
Since ixh is dc, doesn't that mean that d
Right. Yeah.
d is 0?
Oh, what I'm saying. Oh, what I'm saying here. I see your point. Yeah. Okay, sorry. Let me change this thing. Yeah, sorry. There was a. It's just this. So x plus ixh gives you a symmetry of an infinitesimal symmetry of the Coulomb algebra, because if you call this B, then d of B is Lx of h.
Isn't that
Is that
0?
okay?
But I mean, but it is still 0, right?
Oh, what I'm saying. Wait. Because I'm saying because ixh is d of. Yeah. Oh, yes. Sorry, I'm a bit confused here. Let me try to say what I want to say. And of course, my slides are wrong. But what I want to say is the following. Yeah. I understand your point now and why this is very confusing, because it's wrong. So suppose that you have one of these vector fields which satisfies this equation, right? Then what happens for some one form? Right? And then what happens is that x itself is an element in Lie of out of E, where E is determined by H. T plus T star pairing and bracket. and now it's correct, right? This X alone without B field, with zero B field, is a symmetry of the current algebroid because LXH equals to 0. Okay. Just because IXH is D of G. Okay. But now the point is that the current algebroid itself is, yeah, what I'm saying. What is the role of the one forms here? It is not saying more than the vector field is preserving the three form. Okay, let me leave it here. But I just wanted to show you that this this natural condition which appears when you are trying to look for directions where your functional is not moving is related to the Lie algebra of the automorphism group of it. And this is of course true. So this X by itself with zero B field is an element in the Lie algebra of the automorphisms. But there is a more refined explanation related to these one forms which I have to remember myself. But let me move on and continue with the explanation.
Okay.
Okay, thanks. I'm sorry for the mess. Okay. So let me go back to the slides. Okay. And what I want to do, I want to stop sharing and share the slides. Okay, this is where we are. So any further questions about this, or I move on to the general geometry part? Okay, so what I want to tell you about now is about the proof of this theorem, which uncovers this natural symmetries of the generalized Ricci flow. So for doing so, let me skip a bit the preliminaries, but of course, generalized geometry was introduced by Hitchin in this seminal paper in Quarterly. And then the idea for generalized geometry is to do geometry replacing the tangent bundle by the tangent plus the cotangent bundle on the manifold, and replacing the role of the Lie bracket on the tangent bundle by the Dorfman bracket. Okay, so if you play this game, then you will find several natural and interesting geometric structures on your manifold. Another paper which is going to be important for us is this paper by Marco Gualtieri, where he initiates kind of the study of this generalized Riemannian geometry and the role played by generalized connections, which is going to be important for our picture. So let me start by talking about generalized metrics. So the idea now is to try to define generalized Ricci flow as a natural flow on the space of generalized metrics. So a generalized metric on an exact current algebroid is either a reduction of the bundle of orthogonal frames to the maxima compact, which is On cross On, or you can think of it as also as a rank n positive definite subbundle and B plus inside E, or as an orthogonal endomorphism G from E to E, such that G squared equals the identity and this other quantity, so pairing the endomorphism with the pairing is positive definite. So this G in relation to the B plus is just what this is doing is acting as one on B plus on this subbundle, and acting as -1 on the orthogonal complement 4 with respect to the neutral pairing. So let me show you this more explicitly. So if we choose an isotropic splitting of E, then we can identify as before E with tangent plus cotangent. And then we have that a generalized metric can be written in this form. So a generalized metric is going to be the plus bundle is going to be given by x plus gx plus bx, and the minus bundle, which is the orthogonal of the plus bundle, is going to be given by x minus gx plus bx, where here g is a usual metric and b is a two-form on the manifold. And out of this data, you can cook up what is the endomorphism G explicitly, big G, and it's given by this formula. So if you want to think of it as, it's like doing a B-field transformation or conjugating by a B-field transformation, this natural endomorphism cook up out of the Riemannian metric. Okay, so I'm going to assume that my metrics are Riemannian. One important fact about generalized metrics is that they determine a preferred splitting. And this is related to this B field which appears here. So in other words, a generalized metric determines a preferred way of seeing the Courant algebroid and its bracket, or if you want a preferred representative of the cohomology class or the isomorphism class of the Courant algebra. So the splitting, if you fix one splitting, then the preferred splitting is going to be given by x minus bx, where b is the two form which appears in this formula. And this is the preferred H in the cohomology class. So recall here that the Courant or the Dorfman bracket is given by this formula, where H0 is a prescribed cohomology class, a prescribed element in the cohomology class determined by the fixed splitting that we are using, just the splitting sending T to T plus T star here. Okay, so I'm going to give you the idea, and then I think I'm going to stop because I'm kind of out of time. So the idea is that I want to understand generalized Ricci flow as generated by natural vector field in the space of generalized metrics. So from what I told you before, the generalized Ricci flow, a generalized metric is given, if I fix an isotropic splitting, is given just by a pair GB, where G is a metric on the manifold and B is a two-form on the manifold, right? So using the defining equations of the endomorphism, of this endomorphism here, the fact that G is an orthogonal endomorphism of the bundle tangent plus cotangent, and that G squares to the identity, what I get is that the tangent space to the space of generalized metrics is given as follows. So the tangent is going to be given by endomorphisms, G phi. And now I'm going to describe the conditions in terms of phi, of this phi. So phi has to be in lambda 2 of phi, so it means that it is in the Lie algebra of the group of orthogonal transformations of the Courant algebra, and it anti-commutes with the endomorphism which describes the generalized metric. So there are two proofs of this. One is very simple, is just by taking derivatives on the fact that G is orthogonal and that G squares to the identity. So when you take derivatives from G squared equals identity, what you get is this condition here. And when you take derivatives on the condition of G being orthogonal, what you get is this condition here. Okay. G phi, and endomorphism says that phi is in lambda 2. And the more pedestrian way of seeing this is by just taking the formula for the endomorphism in terms of a metric and a two-form and taking derivatives brutally and checking that these conditions hold. Right? You can do these things either way. But this gives you a more explicit description of what is the tangent to the space of generalized metrics. And an important observation that I'm going to use in the definition of the generalized Ricci tensor is that there is a linear isomorphism between the tangent to the space of generalized metrics and the homomorphisms from B minus to B plus, which is given by restricting phi to the B minus bundle. And this is just an artifact of the fact that phi is an element in lambda 2 of A and anti-commutes with G. So it means that anti-commuting with G means that it exchanges B minus with B plus. And this condition here, it means that whatever information phi has when restricting it to B plus is the same as when I take phi and I restrict it to B minus. Okay. So this is why I get this linear isomorphism. Okay. So let me mention this thing and I stop because I think some people have to leave, right?
Actually, well, yeah, I noticed it's already a little bit past 2 now. I mean, we didn't really explicitly discuss it, but I mean, well, no one's left. I don't think so.
Let me
but
finish.
Maybe it's probably right to stop anyways.
Okay. So let me finish in this slide, and then next day I explain in detail the construction of the generalized tensor. But this is, let me finish with this.
Of course, yeah.
So the idea is the following. So in order to prove that theorem that I told you, that these quantities, generalized Ricci flow and the generalized Einstein-Hilbert action, are invariant under generalized diffeomorphisms or under this group of automorphisms of the Courant algebra, I need to interpret the quantities which appear on the equations and on the functional as natural curvature quantities in generalized geometry. And then I'm going to define two quantities which are going to play an interesting and important role. One of these quantities is the generalized Ricci tensor, which I'm going to regard as tangent to the space of generalized metrics. The other one is the scalar curvature, which is going to be the integrand in this generalized Einstein-Hilbert action. And quite surprisingly, I will explain why next day, but quite surprisingly, if one tries to just follow the path that one usually uses in Riemannian geometry, then this thing cracks, it doesn't work. So what do you do in Riemannian geometry? In the Riemannian geometry, if I give you a Riemannian metric, in order to look up curvature quantities, what you do is to define a Levi-Civita connection, right? And this connection is uniquely defined by the two properties that it is metric compatible and it is torsion free. The interesting thing about generalized geometry is that having a metric compatible torsion free connection in the right sense, it does not determine the connection uniquely. And one of the things that happens is that one needs to introduce a new ingredient, which is a divergence operator. Once you do that, so once you fix this divergence operator, then you are able to introduce these curvature quantities. So what is a divergence operator? So this is the additional ingredient that you need on top of a generalized metric to define curvature. So a divergence operator is a map from a smooth sections of the tangent plus the cotangent or your abstract exact Courant algebra into smooth functions, satisfying a Leibniz rule with respect to the anchor map. So the divergence acting on the function times a section of E is f div E plus the anchor applied to E acting on F. And to see one explicit example, if you take a generalized metric, recall that this determines a preferred splitting. So I can write E, my section of the Courant algebra as X plus T, a section of tangent plus cotangent, in the preferred presentation for the Courant algebra given by the generalized metric. And then this generalized metric determines a divergence out of this formula that I'm going to call the Riemannian divergence. Div G of X plus T is trace of nabla, which is the same because nabla G is the Levi-Civita condition. This is torsion free. So this is the same as Lie derivative of the volume divided by the volume. And it is interesting the way these operators appear, because in a sense they are keeping track of conformal geometry on tangent plus cotangent. So you see, on tangent plus cotangent, I have an ambient metric, an ambient pairing. And at least a priori, if I'm doing generalized geometry, I need to do everything in a way which is compatible with this pairing. So there is no natural way of rescaling a metric, doing conformal rescaling of a metric. Nonetheless, these divergences do something very similar to what a Bailey structure does. So let me explain what this is in the whiteboard. So what happens? So what is a Bailey structure on a manifold? Well, you need to fix a conformal class. And then a Bailey structure is a map from elements in this conformal class into one forms. We take a metric and associate some W. And the definition or the defining property of this Bailey structure is that if I rescale my metric by some function, then this has to be W of G plus D of F. These Bailey structures are a natural device to keep track of the change of Levi-Civita connection when you do conformal rescaling of a Riemannian metric. So let me now show you what happens with the Riemannian, with the divergence in the Coulomb algebra. If I take a divergence in my Coulomb algebra, which is a map from here to here, then I can cook up a map from the space of all generalized metrics into the sections of V, which associates to a generalized metric G, diff of my divergence minus the Riemannian divergence of this generalized metric. So recall that diff G x plus C is Lx of the Riemannian volume divided by the Riemannian volume. Well, this property here satisfies something this W here satisfies something analog to the properties of a Bailey structure, which is that if I take my W and I evaluate it explicitly in a generalized metric hookup out of a metric of the form e to the fg and a 2 form B, then this thing is going to be W of GB minus df dot. And it has an n here. N is the dimension of the manifold. So you see these differences of the given divergence minus the Riemannian divergence has the same effect as a Bailey structure on the manifold in the sense of conformal geometry. Okay, so to finish, I just want to mention.
Sorry, do we have the anchor map there in the last formula?
Oh, can I? Yeah, let me show. Yeah, of course. I wrote it. Where am I? Yeah. What do you mean here?
No, in the last line. So you're pairing this df with a section.
Yeah, this is pi star of df. Yeah.
Thanks.
Yeah, this is minus n pi star of df. Yeah. And here I'm identifying E with E dual. So really the difference of two divergences is an element in the E dual. I'm identifying that. So this is, in this sense, this is key of conformal geometry because it's doing the same thing as a Bailey structure does on a manifold. So to finish, just let me show you that, let me mention that once I have this device of divergences, then I can define this generalized Ricci tensor and this generalized scalar curvature. So associated to a pair generalized metric and divergence, there are curvature quantities, generalized Ricci tensor and scalar curvature, such that the generalized Ricci flow and the generalized Einstein-Hilbert action are given as follows. Okay, so this is the evolution of the generalized metric is given by -2 times this generalized Ricci tensor, and the generalized Einstein-Hilbert action is given by the integral of the generalized scalar curvature. So this is what I'm going to explain in more detail next day before we move on to the basics of generalized Ricci flow from the analytical point of view. Okay, so I finished. I'm sorry for the time.
Okay, yeah, thanks, Mario. That was really nice. So yeah, thanks. Any more questions for Mario?
Just a short comment. I think I know what was wrong in the previous slide of the Lie algebra of the automorphism group of the current algebroid.
Yep. Yep.
Can you go to that slide?
Yeah, sure. Yeah.
So yeah, I think you want the contraction of H with X to be Xi, and then the pair X Xi is an element of the Lie algebra of the automorphism group, because in that case,
No, but the element in
the
the
Lie
algebra
derivative of H along X equals. Sorry, I think I didn't hear you very well.
An element in the Lie algebra. Yeah, I can. So an element in the Lie algebra of the automorphism group needs to be a pair XB, where B is a two form.
Yeah.
So
I'm saying the pair should be X, IXH.
Yeah. I think that's right. That's what you said eventually, I think, at the end, Mario, isn't it?
Yeah, I said so.
I think eventually.
Okay, but I was saying that the yeah, that's true. Yeah. That's correct what you're saying. Yeah, I think so. So if I take X, IXH, then this is an element in the algebra of the automorphism group. And that's it. Yeah.
Okay, anything else? Okay, yeah, so if not, thanks again everyone for coming, and thanks Mario for the nice talk, and he'll speak again next week about this like generalized Ricci curvature. So yeah, thanks Mario.
Okay, thanks, bye.